So we're going to talk about free energy diagrams. And first we're going to just kind of remember all these little bits from free energy diagrams. What's a free energy diagram? It has potential energy, has this reaction coordinate, kind of where the reaction progresses. It has starting materials. It tells you something about the starting materials, energy. It has product energy. It tells you something about that. That's defined as delta H. There's an activation energy, the energy it takes to get to the transition state where the bonds are being formed and broken. All right. So the transition state is that middle point where we show those mechanism arrows. That's where the transition state is. And then, of course, you've learned about calculating delta H and delta G. You've learned these things. We'll kind of review this in a different context now. So this is a one-step reaction. There's no intermediates, just one transition state. Every transition state you have tells you how many reaction steps it has. So this is a one-step reaction. What kind of reaction is this? This is a SN2 reaction. Nucleophilic substitution bimolecular. Right? Involves two things, SN2 type reaction with one step. Right? Two things, bimolecular, one step. What about a two-step reaction? Two-step reaction, similar to before, only thing now we've added in, we have an intermediate. So this is a two-step reaction. You have two transition states. And now we have an intermediate. Intermediates are things you can isolate. Transition states you can't. Again, you have your starting material energy, your product energy. In both these examples, the product was at a lower energy. So it's an exothermic reaction, they call it. The height of the hill tells you the first activation energy from starting material to the top. The second activation energy is from the intermediate to that second hill. And then on down. What kind of reaction is this? This is actually an SN1 reaction. A substitution nucleophilic unimolecular. The rate only depends on this first step, the highest hill, right? Highest transition state. The rate depends. That's when the leaving group leaves and you form a carbocation intermediate. So this is the SN1 reaction, which you've seen before. One of the common things, a reaction rate with a catalyst. People will say a catalyst lowers the rate or decreases the rate. That is false. That is not true. That's not what a catalyst does. A catalyst offers essentially an alternative pathway. Right? It gives you a different way to get to the products. It doesn't change, right? Without a catalyst, this actually changed the activation energy? Absolutely not. A catalyst offers a different pathway for things to go through, a different transition state. Right? Essentially, it's a completely different reaction. It gets you from the same starting material to product, but it's a completely different reaction, different mechanism. That's why we care about mechanisms a lot too. And of course, it gets regenerated and it doesn't get changed at the end. We all know those things. Okay, lots of words. Something called the Hammond postulate. Super easy to understand. All the Hammond postulate really says is it looks at the transition state and it says, is the transition state closer in energy to the reactants or is it closer in energy to the products? Right? So that tells us something about the transition state. So the Hammond postulate looks at the transition state and says, if it's closer in energy to the reactants, it's more like the reactants. If it's closer in energy to the products, the transition state is more like the products. That's all it's saying here. Right? That's all it's saying. So the example they give, right, just like we just talked about, the SN1 versus SN2, versus SN1. SN2, usually the transition state is closer in energy to the starting materials. Right? So the transition state is more like the starting materials, the reactants. And in SN1, the transition state is much more like the products. Let's just show the example. All right. Still good? Kinetics and thermodynamics. A kinetics is all about the rate of the reaction. Thermodynamics is all about equilibrium. So I always think, what does kinetics care about? It wants to know how fast. Right? How fast is this reaction going? So it's really concerned with kinetics is really concerned about the transition state energy, the height of the hill, the activation energy. That's what a kinetics is worried about. Thermodynamics is really asking about how much. Right? its thermodynamics really compares the energy between the reactants and the products. It's not concerned with the activation energy. And vice versa, the kinetics doesn't care about the energy of the products. It only cares about the height of that hill, the activation energy. So what does this mean? There's these terms, kinetics and thermodynamics, so now what does it mean? Sometimes you'll get something called the kinetic product and something called the thermodynamic product. So what is the kinetic product? What is that? That's the product that came from the lowest activation energy. Right? That's when they came from the lowest activation energy. It has nothing to do with whether or not that's the most stable product. Thermodynamic product is just the most stable product. It has nothing to do with the activation energy. So in the case I have drawn here, C and D is both the most stable product, thermodynamic product, and it also comes from the lowest activation energy, the lowest hill, so it's also the kinetic product. Is that always the case though? No. Right? Sometimes something that comes from the higher energy will actually give you the lower energy product, and vice versa. Some could come from a low energy transition state but give you a higher energy product. So here's that example. So now if we look at C and D and E and F, which one's the thermodynamic product? Thermodynamics is only concerned about the difference in energy between the starting materials and the products. So the thermodynamic product is C and D. Right? Because that's the lowest energy one. That's all that matters. Which one's the kinetic product? That comes from the lowest activation energy, the lowest hill. That one is E and F. This we would call the kinetic product, because it came from the lowest energy transition state. And then finally this statement, right? Most times, the most stable product comes from the lowest energy activation energy, right? Most of the times that's what it is. But these terms, kinetic product comes from the lowest activation energy. Thermodynamic product is just the most stable product, right? So just be thinking about those types of ideas as we go through some of these things.